In this presentation, we are going to discuss the last part of chapter 4, and what we are going to study today is the thermodynamics, which is one of the branch of the physics, and we will focus in the first and the second law of thermodynamics. The thermodynamics study the relation between heat and mechanical energy. Is how we can convert heat into mechanical energy into heat. And one example of how we can convert mechanical energy into heat is through friction. Then when we rub our hands, then the hands get warm. Means when we are rub our hands, then what we are doing is, in this case, we are moving our hands. This corresponds to the kinetic energy that we know is one kind of mechanical energy, or one type of mechanical energy. Then, but this, when we move our hands, they become warm. And what happened is this mechanical energy was converted into the heat. But to convert heat into mechanical energy, one special device is needed, and this device is called the heat engine. And in these examples, we had a very simple heat engine. We had a container which has a piston here, and on top of the piston we had a weight. Then what happened is, in this part of the container we had some gas. In this case we had air. Then what happened is we add heat to the air, is we heat the air. And what happened is that energy that is transferred to the air increase the kinetic energy of the molecules. And because the molecules now start moving faster, then the temperature inside of the container, the pressure inside of the container will be also increased. And then what happened is this pressure move this piston to add some distance h, some distance, this distance. And what happened is now we are increasing the potential energy of this weight, of this object we had on top of the piston. Then what we are doing is we are converted as heat, that this is what is the energy we are giving to the gas, but this energy is converted into the potential energy because we are moving the weight. Then the laws of thermodynamics describe what happens with the energy as it is transformed into work or other forms of energy. And this is what the law of the thermodynamics explain. Then let's review the first law of the thermodynamics. Then the first thing is this law. One of the statements of this law is each system is a state of the system is identified by some value of the internal energy. Then when we are talking about the internal energy, then we can identify that internal energy of the system by the volume, by the pressure, by the temperature. Yes. Then remember, the internal energy is the energy of the molecules. Then we can identify, depending on the energy, that system we had some volume, some pressure, and some temperature. And is we can identify the state of this system by the internal energy. What happens is the change between any two states of this particular system can be changed in two different ways. Yes, we can change the state, we can change the internal energy of this system in two different ways. If we add heat to the system, yes, if we give some energy to the system, if we increase the energy of the molecules. But the other way, we can change the state of this particular system if that system is doing some work. Yes, means when that system is doing some work, is lose some energy. This is why this is negative here. Yes. Then the change in internal energy, remember the internal energy is the energy of the molecules. Then the change in the internal energy between two different states of some particular system depend on how many energy we add to the system and how many energy is lost by the system or is given by the system. For example, when the system is doing some work. This is the equation is in your book, but here just the difference is they use G value as the mechanical equivalence of heat. Just is the conversion factor. They include the conversion factor between joules and calories in the equation. And for some students is confused to use that equation, then what we can do is we can calculate the values and we can convert at the end, yes, if it's needed. Let's talking about a little more about heat engine. Then these engines were in cycles. Then what happened is these machines start in some state with some particular internal energy. They doing some work and they return to the original state. And this is why the change in internal energy between two states, they equal to 0 because they return to the initial and the final states, they are the same. And this is why the internal energy equals to 0. And what happened in this diagram is the representation of the heat engine. And in these engines, some heat is supplied, some energy is supplied in form of heat. Then part of this energy is doing some work. Yes, it's converted into work. But always in the engines, we will have some loss of energy, and this is in this diagram correspond to the low temperature region. Is the energy we lose when the machine is working. Then this is why the available energy to do work equals to the energy or the heat is supplied to the engine minus the heat is lost in the engine. Then this is the amount of energy or the heat that is available to do the work. And let's now, we had this is the equation we already discussed for the first law of thermodynamics, and we say in these engines this equals to 0. And if this equals to 0, then we can say if this happens is the work equals to the heat, but the heat that is available to do that work. But what happened, we know the heat that is available to do some work is the heat we supply minus the heat we lose, yes, or it's lost by the engine. Then this is why we can represent the work by this equation. Yes. Then if we supply some energy to this machine, part of the machine is is doing some work, but part of this one is lost. And this is the equation that is in your book, but again, G is just the conversion factors. Then if you get confused using this equation, then applying this equation, yes, you can apply the first equation and convert if it's needed at the end of the problem. Then in heat engines, the work done by these engines equals to the energy we supply, or the heat we supply, minus the lost energy. This is we are representing in this diagram also. One of the examples of heat engine is the steam engine, and in this case the water is heated at 100 degrees Celsius. Then the water turns into steam. What happens is the steam expands, and the force generated pushes a piston back and forth inside of the cylinder, and then this motion of the piston back and forth rotating the wheel. And this is how heat is converted into the mechanical energy. And this is the same happen also in coal power plants. Then they use coal to heat the water, and then the water is converted into steam, and this steam passes through the turbine. In this case, turbine is convert the heat into mechanical energy, and then the mechanical energy that is generated in the turbine is passed to the generator and convert the mechanical energy into the electrical energy. But here we are concentrating just in the part where the heat is converted into the mechanical energy. Then just to summarize, we say the one of the examples for heat engine is the steam engine, and in this the heat is converted into the mechanical work. Yes, this is the heat engine is doing. And here we have two examples of heat engines. In this case, we had the engine car and steam train work. Then both are examples of the heat engines. In case of the car, we had internal combustion heat engine, and in case of the steam train, we had external combustion heat engine. And let's now try to solve some problem to apply the first law of thermodynamics. And we had in this case a heat engine that operates with 65 kilocalories. Then probably we can here represent the heat engine as this is. Then here in this part we will represent is the energy that we supply to the engine. Then in this case will be 65. Then here we had H, and we can write here QH equals to 65 but this machine loses 40 kilocalories, and we know this corresponds to QL. This is the low temperature region, and here is Here is 65. Here is 40. Then we want to know how much work did the engine do. Then if we had 65, yes, and we lose 40, we know how much work can do this machine, yes. We know how much work can do. Because if we had 65 and we lose 40, then we had 25 available to do some work. And this is the same we had here. Yes, it's just the application of the conservation of energy. Yes, we cannot create or destroy energy. Yes, the energy should be converted into something. Then this is why here we had 65, we lose 40, but then 25, the 25 kilocalories are available to do some work. Then let's apply the equation. Work and we can 65 calories minus 40, and we know here we had 25.0. Then here the work 25, and we can see what the amount of energy we supply equals to work plus the energy we lose, is 65. Then now, usually when they are talking about the work, then in the book they give the answer in joules, yes, because these are the units of work in the SI system. But we know kilocalories also we know joules are also energies of are units of energy. And let's convert this kilocalories into joules. Then we know we can use this conversion factor. Then we had 25.0, and we know we need to write kilocalories in the bottom. Is the only way we can cancel out the unit we don't want. And then finally we have joules. This is the unit we want. And if we multiply these numbers together, we will get 104,600 joules. And if we write this one with 3 significant digits, and here, I should write this one with 3 significant digits. Let me correct this part. And here also, let me write with 3 significant digits. This is the correct way to do it. And if we write this one with 3 significant digits, then we will have this one like 105,000 joules. And this is one possible way to write the answer. Then also we can see we had 1, 2, 3 zeros. Yes, then we can write this one like 105 kilojoules. And we had 1, 2, 3 correspond to 1,000. Yes, 1,000 is kilo. And we can write 105 kilo. And also this is 2 different ways we can give the answer. And if you need to write this one in scientific notation, then we count 1, 2, 3, 4, 5, and will be 1, 10 to the power 5, joules. And this is if you need to write the answer in scientific notation. And we know the exponent must be positive because it's larger number. Now we are going to discuss the second law of thermodynamics. One of the statements of this law say if the heat can flow from the higher temperature to lower temperature naturally. Yes, we don't need to do anything. Just the heat flowed always in this direction from hot to cold region, and we don't need to do anything. But if we want the energy move in opposite direction from cold to hot, then what happens is we need some engine, we need some machine to do that work. And the machine that doing that work is the heat point. One of the machines can do that work is the heat point. And what happened in this case, if we want to move energy from the cold region to the hot region, then some work is needed. Yes. Then some work is needed to move energy from cold region to hot region. And this is what we are representing in this diagram. And we can see to move energy from this region to this region, then some work is required. Then this is why, and we can express this one using the conservation of energy. Then the energy we can get here will be equal to the work done, for the work done plus the energy we had in the cold region. Yes. And the energy we can get here will be this energy. Then we know work is also related to energy, and is this work plus the energy we had in this region. And this one plus this one equals to the energy we had in the high temperature region. Then also another statement of the second law of the thermodynamics is related to the efficiency of the engine, of the heat engine. Then these are the statement of this law that it's impossible to convert heat completely into the mechanical energy. Why? Because we had some loss of energy in any engine. There's like friction, heat, sound. Then always we will lose some energy. Then it's impossible to have 100% efficiency in any engine or in any machine. Then we can calculate the efficiency of any machine if we divide the work done by this machine divided by how much energy we provide to this machine. The maximum value, if all the energy we supply is converted into work, then we will have the efficiency will be 100% because there is no loss of energy. But we know it doesn't happen. And this is why always the efficiency will be less than 1. Yes, will be less than 1. And the reason is because always we had some energy that is always degraded. Then here in this example, we are summarize the conservation of energy for the heat engine, and we say the work equals the work done by the heat engine equals to how much energy we supply and minus the energy is lost. But in this case, in case of the heat pump, then the energy we can get in the high temperature region, or in this region, will be equals to the work is done by the system plus the energy we had in the low temperature region. We can see these two equations are just one application of the conservation of energy. As this is just is one application of the conservation of energy. And let's now try to solve one problem in which we apply the concepts we already discussed. Then in this case, we had a heat engine, and in each cycle, 350 kilocalories is supplied to this engine. Uneasily jet means that engine loses 220 kilocalories. And let's try to represent that. Then we supply some energy. Part of this energy is doing some work, but part of the energy is rejected. And let's write this here. We had the energy is supply is 350 kilocalories. The energy is rejected is 220. Then we want to know what is the efficiency of this. And to calculate the efficiency of this machine, of this engine, we need to know the work, because the efficiency is the relation between work and the energy. The work done by the engine divided by the energy is supplied to that engine. Then, but we can calculate the work because we know how much energy is supplied to the machine and how much energy is rejected. Then we can calculate first the work. And it will be 350 divided by 350 minus 220. And the work equals to 130. Then now we can calculate the efficiency because we know the work. And now the work, which is 130 kilocalories, divided by the energy is supplied to the engine is 350. And we can see the units cancel out. There is no units for efficiency. Then it's just a number, and we know the number should be less than 1. 1 is the ideal case. Yes? There is no loss of any energy. And if we divide these two numbers, we will get 0.37. And we can write the answer in two ways. We can write the answer like that, but also we can say the energy we can give in the percentage is, we multiply by 100, then we will get 37%. And we can give the answer in decimals, but we can also express this answer as percentage, and just we multiply by 100. Then this is now, you can think this is low efficiency, but in real life, for the real machines, this is actually good efficiency. We can see for the cars, yes, for the gasoline engines, for example, the car, currently the thermal efficiency is about 25 to 50% only in Scotland. Then actually 37 is good efficiency, yeah, in this kind of engines. This is all I had to discuss for today.